Charlotte received the PhD degree from University Catholic de Louvain, Belgium in 2020 after a postdoc at the Institute of Neuroinformatics, UZH and ATH, Zurich, Switzerland. She joined Delft University of Technology, the Netherlands, as assistant professor in July 2020. Her research focuses on neuromorphic integrated circuit design and learning algorithms for adaptive edge computing. She received the Best Paper Award at the IEEE ISCAS 2020 conference, as well as the FNRS Nobel Lab Scientific Award, the FNR IBM Innovation Award, and the UC Leuven ICT Team Best Thesis Award for her PhD. She serves as TPC member for the TinyML Research Symposium and for IEEE SS Circle, IceFeld, and DATE conference. Welcome, Charlotte. Thanks for your time, and the floor is yours.
Thank you so much, Danilo, for the kind introduction, and thanks as well for the TinyML on-device learning committee for inviting me. So in this talk, I'm going to talk about how to merge insights from artificial and biological neural networks for neuromorphic intelligence applied to on-device learning. So there are going to be three parts in this talk, three main questions. One is there are tight synergies actually between neuroscience and AI, but what is the right perspective and what is the right starting point to make the best out of these synergies? Second is why should we actually bother with neuroscience? What can neuroscience bring to us? And third, based on the answer to the two previous questions, how can we morph these questions into interesting solutions for on-device learning? So that is the plan for my talk. So first part, the tight synergies between neuroscience and AI and what is the right perspective. So we have actually bidirectional synergies between neuroscience and AI. And so from neuroscience to AI, this is really about science. This is a bottom-up approach whose aim is to understand how the brain is processing and then to uncover what are the key computational primitives of the brain and then to apply them to actual AI workloads. So for example, some of you might be familiar with spike timing dependent plasticity, which is a bio-inspired rule. We are going to go over this later on in the talk. But this is really about a bottom-up neuroscience-driven approach. On the other hand, you have engineering-driven approach, which are really top-down. So you start actually from the working AI algorithms, and then you try to make those more bio-plausible. So for example, the whole school of bio-plausible backprop is belonging to this school of thought. But the problem is, what is the right perspective? Because it's still a bit unclear whether you should go the bottom-up way or the top-down way. So the standpoint that we'll take in this talk is that actually neuromorphic hardware offer a very interesting middle ground to uncover some new synergies. So between AI and hardware, most of you are already familiar with the fact that AI without hardware is completely unsustainable. Definitely the TinyML community is the most aware of this problem. So I'm going to be very short on that because most of you are familiar with this graph, which is showing the training compute evolution over the years. So you have here traditional machine learning workloads. Now it's getting even worse with the transformer era, where the training compute requirements are multiplied by approximately 750 times every 2 years. In comparison, Moore's law is still struggling to achieve the 2 times every 2 years. So we have a big problem. At some point, we cannot scale the GPUs over farms forever, and we need hardware-aware AI algorithms. But the problem is that actually between neuroscience and hardware, we often talk much less about what are the synergies. And so this is going to be the second part of my talk. What should we bother with neuroscience and what can neuroscience bring to us? So let's start with the spike time independent plasticity algorithm, which I have mentioned earlier. Because when it comes to synaptic plasticity and learning neuroscience inspired, this is usually the starting point that is adopted. Whether it is the right starting point is actually another question, and we'll come back to it. So for those of you who are not familiar with these algorithms, here's an illustration with 2 neurons. Every time you have a presynaptic spike, if it is before the postsynaptic spike, this is what we call a causal relationship, and you will enforce the correlation by potentiating the synaptic weight. But if the relationship is anti-causal, like the postsynaptic neuron fires before the presynaptic neuron, then you will depress your synaptic weight. This is an anti-causal relationship. But this is as simple as that and has been observed in the brain. And the usual key advantage of why people would like to investigate spike time independent plasticity is because it is a local learning rule that relies only on local information. And from a hardware point of view, that's nice because you only need to access information from locally available memories. So instead of a big centralized memory where the access cost is much higher. So this is one way to go. There are actually a lot of variants of synaptic plasticity rules in the brain. So here I don't want you to understand actually the details of this learning rule, which is called spike-dependent synaptic plasticity, or SDSP for short. Just want you to look at the mechanism. It's a bit different. Here, every time you have a presynaptic spike, you look into the state of the postsynaptic neuron at the time of the presynaptic spike. This is the main difference, but otherwise the two learning rules typically work roughly the same, have the same learning performance. And both are local. They only rely on presynaptic and postsynaptic information. So how should you choose? So actually here is where hardware comes in. So let's try to implement both learning rules in, for example, with a digital synapse, digital circuit implementation. And here for STDP, you see that there's one thing here that we need to do is time window generation. So you have a shift register. You need to keep in memory when the presynaptic spike occurred to compare basically the arrival time with the postsynaptic spike. And you need to do that inside every single synapse. So this is really scaling with the number of weights and not the number of neurons. On the other hand, if you look into spike-dependent synaptic plasticity, every time you have a presynaptic spike, you look up the state of the postsynaptic neuron at the time of the presynaptic spike. So inside the synapse, there is not really a computation that you need to do. Everything is done in the neuron and shared among all the incoming synapses to that neuron. So that makes a huge difference. And this is because the fact that both learning rules are local is definitely not the end of the story. The thing is that they are both local in space, so locally available information between two neurons, but only SDSP is local in time. Here, you need this time window generation, which is actually very expensive. So actually going to hardware allowed us to uncover some synergies or some more insights, which are twofold. One, it hints toward more biologically plausible mechanisms, because actually voltage-based learning rules as this one here, looking up the state of the postsynaptic neuron, is actually more bioplausible. You can look into neuroscience research there. But it also leads to hardware that is much more efficient. So this actually, we went ahead, we selected this learning rule, we implemented hardware based on this. So this is the Odin Neurosynaptic core, which is fully open source. So this is fully digital. The Verilog code is available online. You can prototype that in an FPGA if you want. And it achieved at the time of publication a record synaptic density, an energy efficiency that is competitive with analog mixed signal designs. We talk a lot about analog computing and its efficiency. And here we show that by following simple principles and making sure to access only local information, you can actually come quite close to the efficiency of analog designs. And also you have a large feature set, including among others, the synaptic plasticity, which allows you to do on-device learning. So we even show that this is scalable. So this is a quad-core neuromorphic processor that is based on these principles. But the key thing is that actually exploiting spike time independent plasticity to reach competitive performance on machine learning workloads is actually quite difficult. This is a nice feature set, which is actually quite painful to exploit. So actually now we can go the other way around. So we have been going from neuroscience to AI. Now let's go the other way around, from AI to neuroscience. And so this is now a top-down approach. And now, given that we have to start from the workhorse of deep learning, we have to start from backprop. So let's now, the end goal is that bio-plausibility is really the end objective. So let's make backprop more bio-plausible. And we have two key issues for which backprop is not biologically plausible. One is the weight transport. So this is the fact that during training, you are using the forward, in the forward pass, you're using the weight matrix there. But during the training phase, so while you backpropagate the gradients, you have to use the transpose of this matrix. So in terms of memory accesses, this is not so easy in hardware. In terms of biological plausibility, this is an issue because it would mean that synapses are bidirectional, and this is clearly not the case. On the other hand, you have update locking. So before, for example, updating this weight matrix here, you have to go the full forward pass followed by the full backward pass. So this is really two-phase learning. And the problem is that from a hardware point of view, it needs a lot of buffering. And from a biological plausibility point of view, this is problematic because there is no such two-phase learning in the brain. This is everything happens in parallel and in real time. So we have to work on these two problems to make backprop more bioplausible. So in the state of the art, there's this feedback alignment algorithm, which is getting quite famous. The only difference is that during the backward pass, you are using a fixed random connectivity matrix instead of the transpose of the weight matrix. So this allows you to release the weight transport problem. But as you can see, you still have update locking because you still have to go this full forward pass followed by full backward pass. There's also direct feedback alignment, roughly the same principle, except that now you are using fixed random projections, so fixed random connectivity matrices here, of the final error. So this is also releasing the weight transport problem, so no transpose of the weight matrix of the forward pass there. But the problem is that it still doesn't solve update locking, although the latency to update in the backward pass, you see here, there's a shortcut. So if you have a deep network, you have direct connection from the output to the deeper layers here. So yeah, you have less update locking, but you still have these two-phase learning. And so we got an idea. What if, instead of the error here, we were only using the sign of the error? And then you have a very interesting property, which is that for classification problems, you can actually release update locking. So let's see how it works. You have this target vector here. And for classification problems, this is just a one-hot encoding of the classification label. So if you are writing the formulation of the error, you have that in the end, at the end of the network, you typically have a softmax activation layer for classification. So it's strictly bounded between 0 and 1. So you have this target vector here, 1 for the correct class and 0 for the incorrect class, minus something that is strictly bounded between 0 and 1. So what that means is that the sign of the error is actually known in advance for classification problems. It will always be positive for the correct class and always be negative for the incorrect class. So what that means is that you do not need to wait for a full forward pass to get this information. You already have it in advance from this target vector, which you have here. So the algorithm that we propose is called direct random target projection. We now just use a fixed random connectivity, a fixed random projection of the target vector here as a surrogate for the layer-wise gradients. So you see the mechanism is similar to DFA, but it's a proxy for the sign of the error. And this allows us to release both the weight transport and update locking. So we had bio-plausibility as the end goal. And the nice thing is that now we can look into neuroscience research and we can find that in the cortex, there are some output-independent target signals. So I'm not saying that the RTP is the algorithm that the brain is using. It aligns with some of the mechanisms that the brain is using. But doing so, we have also released the computational and the memory cost of these algorithms, up to the point that here we ended up with a purely forward algorithm. So there's a lot of talk actually at the moment since the forward algorithm proposed by Hinton. Actually, DRTP is a purely forward algorithm. You only rely on locally available and forward information as well. So actually, you can implement that on a chip, and you can demonstrate that this is indeed a low overhead scheme that allows you to do on-device learning. So here, this is what we demonstrated with this chip, only about 15% overhead in power and in area. And actually, this is really nice because in this event, we also have Georgia, who's going to talk right after me. And he's doing basically a more evolved version of the RTP in her scheme. So this is really nice that in this event, you can see the whole evolution of how these forward algorithms are training too. So to summarize, we have gone both the bottom-up and the top-down way. And the thing that I would really like you to remember is that hardware efficiency and bio-plausibility are often two sides of the same coin. So this is what we have uncovered here. In the bottom-up way, we have seen that designing efficient hardware hints towards bio-plausible mechanisms. And on the top-down side, we have seen that bringing AI closer to neuroscience leads to hardware efficiency. So this is actually the synergy that we wanted to have when I mentioned, okay, what is the synergy between hardware and neuroscience and allows us to close the loop with AI, is that actually it is a quite natural synergy. They are two sides of the same coin usually. So we have answered the perspective point of view previously, hardware as the middle ground, but what is the right starting point? So now I can actually summarize the main takeaways. First part of the talk, we have gone the bottom-up way. And so this bottom-up neuroscience-driven approach, it is great for analysis by synthesis, so building to understand. You actually build, for example, STDP in silicon to understand how the brain works by trying to actually make your chip work. But the big problem is that for engineering solutions, this is really difficult to scale efficiently to real-world problems. And by efficiently, I mean more efficiency than well-proven machine learning techniques. So on the other side, with the top-down way, we have seen that actually the top-down driven and engineering-driven approach starts from working solutions to real-world problems. So we don't have this problem here anymore. But the big question now is, what is the right salt and pepper from neuroscience that you need in order to achieve a competitive advantage and make your algorithm actually more efficient? So yeah, we are a little bit stuck here between the synergies of these two approaches. And so the thing that the second standpoint that I'll adopt in this talk is that to make the best of the two worlds, which we talk about as neuromorphic intelligence, we should adopt a top-down driven approach, but feeding it with insights from neuroscience thanks to the bottom-up approach. So let's see concretely, that might sound a little bit abstract to you right now. So this is going to be the third part of the talk. How can we morph these questions into interesting engineering solutions for on-device learning? So we need a concrete use case, the one of on-device learning, but let's see one that is particularly challenging, which is the fact of on-device learning over second-long timescales or without external memory. So to do so, the workhorse of deep learning is backward through time. And we have a very big problem when dealing with temporal data. So let's assume you have a sample of 1 second. You have a temporal resolution of 1 millisecond. So that means that you have approximately 1,000 samples here over time for your input. And for each of them, for backprop through time, you need to keep in memory a copy of the state of your network until you reach the final error, and then you can backpropagate the gradients through the entire network dynamics. So this is a process that is called as unrolling in time. This leads to actually very big effective depth for the network. And to give you an order of magnitude, the current learning integrated circuits for static stimuli are limited to approximately 3 layers, because from a memory point of view, this is really difficult to handle more. So this is leading to intractable memory and latency requirements. And this is why so far no end-to-end on-chip solution has been proposed to date. And beware, by the meaning of end-to-end here, I mean no external memory. So because otherwise you could say, yeah, GPUs do it, but indeed GPUs rely on external memory. Here we would like to have it as low cost as possible and avoid the cost of accessing external memory. So typically, for example, for wearables, you have a super tight power envelope. So let's get rid of external memory, but then how do you do on-chip learning over temporal data is the big challenge. So let me rephrase it. The key challenge that we'll look at in the second part of this talk is end-to-end on-chip learning over second-long timescales while keeping a fine-grained temporal resolution. And by fine-grained, I mean, for example, millisecond temporal resolution for second-long timescales. So let's see how we solve that. And obviously, the right starting point that the brain doesn't do backward through time. So let's see what the brain could be doing. So backward through time is referred to as backward mode training. You wait for a final error and then you backpropagate the gradient through the entire network dynamics. And this is why you need to keep in memory all time steps. On the other hand, the brain is likely to work with actually forward algorithms, one of which I mentioned earlier with the RTP. Another one is EPROP, which has been proposed in this paper, and allows to do forward learning with temporal data. So how EPROP works, it actually works as a simplification backprop through time. Very simple simplification, actually. You just rephrase it as a product of two terms. One that is error-based as a learning signal here. So you see learning signals are error-dependent terms, and the only approximation of EPROP is to assume that this term is fully available locally in time. This is the main simplification done by EPROP. And times another term that is here called an eligibility trace, which is a per synapse term that basically represents the importance of every single synaptic weight on the network output. But the interesting thing is that this is a forward term that is computed, as illustrated here, exclusively forward in time and is not dependent on the error. So the nice thing with EPROP, you see it's local in time. You only need to keep in memory the current time step. So going from one to the other, you have that biological plausibility goes up because synaptic eligibility traces are supported by biophysical evidence. You have that space and time locality goes up, and this is why the on-chip memory requirements are slashed, because you only need to keep in memory the current time step. So actually, EPROP is not fully amenable yet to a fully on-chip implementation. So let's solve basically the few remaining challenges together. And for now, let's agree on actually the actual network architecture that we'll take for the rest of this talk. This is a spiking recurrent neural network. So why spikes? I'm going to come back to it a little bit later on in the talk. But for now, EPROP was proposed basically as a bio-plausible approximation of backprop through time. And so they adopted a spiking model. But let's see why spikes are interesting from an engineering point of view slightly later. I'll come back to this. So you have a spiking input. Typical model for spiking neural networks is known as leaky integrated fire neural model. So this is just a leaky integrator. Every time you get an input spike, you integrate and then you leak back to zero. And when you cross a firing threshold, you fire up a spike at the output of your neuron and you reset the neuron here. At the output, we take roughly the same model, except that we don't take a spiking output for the simple reason that we would like to define the error without spikes, because spike-based definitions of the error tend to be a little bit ill-defined. So we want to work with a continuous representation. This is otherwise the only difference. So we also need a task to actually monitor the performance of our algorithm as we do the algorithmic modifications. And this is actually a task that is typical of neuroscience models. This is called that delayed supervision navigation task. So we have a rodent moving along a corridor, and then it has to decide to turn left or right in the end. It sees cues on the left and on the right. For example, it sees here more cues on the left than on the right. Then it has here a cueless phase, and it has to maintain a working memory to take the right decision to turn left or right, depending on previous cues. So this is actually a difficult task to solve for the simple reason that if you try to solve this task with this network with a backprop through time, so vanilla backprop through time, no simplification, the network is just unable to pick up and learn how to solve the task. And the error just doesn't go down. So what is happening is that, strangely, if you're using a slightly more fancy neuron model with, for example, slow adaptation of the firing threshold, then suddenly the network is able now to learn to converge. So what is happening is the fact that with a simple leaky integrated fire neuron, which typically in the brain has a 20 millisecond leakage time constant, you just don't have the temporal dynamics that are necessary to solve this task over second-long timescales, because this is really a task that unfolds over seconds. On the other hand, adding just low firing threshold adaptation over hundreds of milliseconds allows you to give to the network sufficient long temporal dynamics for backprop through time to learn how to exploit these and learn how to solve the task. But the problem, and here you'll have to believe me because I won't do the math, is that the eligibility trace formulation for a simple leaky integrated fire neuron is super simple. This is just a low-pass activity filtering, just a low-pass filter. But on the other hand, this is a super complex per synapse multi-timescale filtering. In other words, on chip, this is intractable. So what do? You have that this one doesn't work, but is simple. You have that this one works, but is too complex to implement. So now actually is the time to leave neuroscience and to go for an engineering approach. We just take leaky integrated fire with a configurable leakage up to seconds. And membrane potential leakage up to seconds is not biologically plausible. You won't find that in the brain, but it allows you to solve both challenges. So this is the main step there. So then the main step is to write the EPROP equations for the leaky integrated fire neuron model. But here, for the sake of time, I have to skip it, but I will just provide the main IDs there. The vanilla EPROP formulation relies on the sum over all time steps of these contributions, but this is not biologically plausible. Like, you need to sum all the contributions of EPROP in a separate memory before applying them to the weights. This is not real time, so we can get rid of it. As long as the learning rate is small enough, we can do the updates per time step, and that works just fine. On the other hand, you have that this eligibility trace term needs a little bit of rework to completely decouple space and time locally. And we show mathematically that this is a negligible simplification compared to the simplifications that are already done in EPROP. So actually what we end up with is something that is fully local in space and time. And we have seen earlier in this talk, thanks to STDP against SDSP, that space and time locality is everything when it comes to efficiency. So the last thing that we need to do, last step here, is that we actually have to quantize the weight, and we show that basically, thanks to stochastic weight updates, we can reduce the weight resolution to only 8 bits. And this is not like quantization-aware training, where you keep a full resolution copy of your weights separately. Here, everything takes place on the device. So also during training, the weights are only 8 bits. You do not have a full resolution copy anywhere. So this is the resulting performance. You have here your baseline backprop through time with an adaptive leaky integrated fire, which we have seen is completely intractable here in green. And here is a chip measurement. from our modified EPROP scheme with a long leakage time constant for the leak integrated fire neuron. And we see here that it's competitive with the backprop through time trained network of ALIF neurons. And the very nice thing is that this scheme that we propose, thanks to the simplifications we have made, we can reduce the memory overhead to only less than 1% of the inference-only network. So you have an inference-only network, you add 1% memory overhead, and this network is now able to learn over second-long timescales, which was the challenge that we were not able to solve beforehand. So this is the 1% memory overhead is a very important claim of the work. So now let's summarize basically what we have done with this methodology, that top-down should be fed by insight from the bottom up. So we have started with a working engineering solution, which is backprop through time. It is not hardware tractable, it is not bio-plausible. So we have looked into neuroscience and we have seen that eligibility trace is the key thing that actually can help solve these two challenges. The combination of both is EPROP. But EPROP by itself is not yet hardware efficient and doesn't work on long timescale without an extended network model. So we look into neuroscience, we see that threshold adaptation is key, but this is actually not hardware efficient. So now we go back to engineering. We take just a simple configurable leak integrated fire neuron. With a little bit of rework for space and time locality, we end up with a simplified EPROP scheme. So now we just have to implement that on chip. And so this is the Reckon chip that I'm showing here, also fully open source, so you can also prototype that on FPGA if you want. It's a tiny chip, only 0.5 millimeter squared of silicon. I want to emphasize no external memory. And so here at the system level, you have that the Reckon chip doesn't care what sensor you connect to it. It can be a spiking neuromorphic retina, spiking neuromorphic cochlea. So now I'm coming back to what I have mentioned earlier, the fact that spikes are also useful from an engineering point of view. Spikes are useful for event-driven and sparsity-aware computation. This probably you already know, but it's also useful for sensor-agnostic raw data processing. And this is great because if you do that at the edge, you can just end up with a chip that is fully task-agnostic in terms of processing and learning. So to demonstrate that, and that's going to be the last slide of my talk, we have selected 3 benchmarks, one for vision, one for audition, and one for navigation. For vision, we have this IBM DVS gesture dataset. So, for example, rolling arms, clapping hands, this unfolds over 6 seconds. For audition, we have taken this spiking cochlea dataset for keyword spotting. This unfolds over typically 0.5 second. And we have this navigation task that we have already mentioned. And we have that for all of these, Reckon has learned to perform these tasks from scratch with reasonable accuracy. Actually, this is quite good for the edge, about 90% for all of them. But the really nice takeaway is that for all of them, including learning, you can learn to solve these tasks within less than 50 microwatts. So this is really something that is compatible with a power budget for wearables. So the key takeaways at the end of this talk that I would like you to remember, that with the Reckon chip, we have merged AI, neuroscience, and hardware to achieve end-to-end on-chip learning over second-long timescales, while keeping a millisecond temporal resolution, which was a yet unsolved engineering challenge. We have provided a low-cost solution with 0.5 millimeter squared of core area, less than 50 microwatts for training at 0.5 volts, and thanks to 1% memory overhead compared to the inference-only network. And also we demonstrate task-agnostic learning with a spike-based encoding toward user customization and even full chip repurposing at the edge. So this is a nice outline for neuromorphic intelligence, and this is really supporting the use case of on-device learning. So to close this talk, I have since then moved to TU Delft, where I'm assembling my own team. So we are looking into neuromorphic IC design, bio-plausible training algorithms, and even system-level optimization. And so why not you? Because we are going to open a few positions just a few weeks from now, so by the beginning of June. So if you're interested, feel free to reach out, even if you have questions on this talk. So this is the overall list of references that I have used, 2 main ones being the Reckon chip at ISSCC, and also this review, which was just accepted for proceedings of the IEEE. So this is going to appear a bit later this year. Thanks a lot for your attention.
Thanks a lot, Charlotte, for your outstanding speech. It was very, very interesting. And personally, I was impressed by the figure you shown in the summary. I know you are busy because you needed to attend to another meeting, but there is a question. I don't know if you have time to reply. There is a question from one attendee. he wrote 50% is rather low compared to 750. Does it show that there is a limit to the DT digital architecture? Is digital a solution?
Okay, so I see where the 15% comes from. It's from the reckon chip there, the spoon chip there. So let me call there.
Yeah.
I'm just not sure what the 750 comes from. So this I'm not exactly sure. But 15% overhead at the edge, if you can afford to do full inference and you add about 15% overhead in parallel area to do full on-chip learning, this is typically something that you can afford. And similarly for the simplified EPROP scheme that I'm talking about later on, you can afford a 1% memory overhead to do on-chip learning at the edge. So then whether you go digital or analog is mainly a question of time to market. So I'm showing here, in terms of research, you can have very convincing proofs of concept, which lie about less than an order of magnitude away than the more efficient mixed signal solution. So actually, this is in the very last slide, and I have skipped a little bit fast for the sake of time because I was a little bit over time. But we are looking mostly into digital chips, but we are also going mixed signal. But we are convinced that the right way to go is to first do the proof of concept digitally, and then you can make it mixed signal to gain approximately a factor 10 to squeeze the last bit of performance. But indeed, with a fully digital chip, you can already have very good performance if you follow the full locality in space and time and local memories.
Thanks, Charlotte. Just a quick question, another quick question. Any idea for co-design spiking neural network with front-end sensor?
Yeah, this is a very broad question. So perhaps the best slide for this is the synergy that was shown a little bit later on there. So this, I'm convinced that this is a very nice advantage of spikes. This is a sensor agnostic representation. So here I'm demonstrating a separate chip that connects to any kind of spiking sensor. So it can be spiking retina, can be spiking cochlea. But actually, what is going on in the IC design field, you have also in-sensor computing. And so that's a very nice avenue, actually, knowing the synergy of this intermediate spike-based representation, which is sensor agnostic. This is indeed a nice avenue for in-sensor computing. So what are the synergies there is definitely among the things that actually we would like to investigate in the near future.
Certainly, Charlotte, your presentation makes possible in-sensor AI computing. So the figures and your study were impressive, and I think interested a lot for the community. So very much thanks for your contribution and your outstanding speech. And
Thank you very much for inviting me.
Again. It was a pleasure, Charlotte. Hope to see you soon. All the TinyML operations are possible thanks to the strategic partners, which are providing the support and commitment to make and to keep successful all the operations, the different events that TinyML Foundation organizes. So thanks to IZIP, Analog Devices, Arduino, ARM, BrainChip, Edge-Impulse, Dreamwave, Technology, Groverty, IBM, ImageBob, Infineon, Innatera, Microsoft, Nota AI, NXP, Pauling Technology, Pixel, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, STMicroelectronics, Synaptic, Syntian. Then our executive strategic partners, Edge-Impulse, as I said, Qualcomm, Syntian, the Platinum one, which are Renesas, then Aetrios. Gold strategic partners are Analog Devices, Arduino, ARM AI, Infineon, Innatera, Microsoft, Sensimil, STMicroelectronics, Synaptics, and the silver strategic partners, as I said before, IZIP, BrainChip, Dreamwave Technology, Groverty, IBM, ImageMob, Nota AI, NXP, Pauling Technology, Pixel, Schneider Electric, and Silicon Labs. All the rights are reserved to the TinyML Foundation. And thanks again for your time, for your patience, also the extra time.